Okay. So thankfully we are getting down to the end. And looking at the schedule of what's to be covered. So this week I have on tap the last of Chapter 6 on eigenvalue problems and the SVD. And then next week I have just tiptoeing, and I really do mean tiptoeing, into statistical learning, and there'll be a Canvas quiz on that, but not a regular homework. And then for the week after that, which is the last week of classes on the schedule, I don't have anything. It just says to be announced. So I've decided that because I think it's safe to say that we're all, students and faculty alike. And of course, a lot of you are students doubling as faculty too, that we are all just kind of over it. And therefore, I will not cover anything new during that final week. I will be around, and certainly we can use the time for because of course I know a lot of you will have homework piling up that hasn't been done yet, and has to be done by the end of April. So certainly I'll be available for questions about that, or if you don't want to bring up anything at that time, then you need not show up. So we'll just um, you know sort of let things ramp down so that you guys can focus more on getting the last assignments done. And I figured I wouldn't get any pushback about that. So okay, so really these this week and next is the last of new material. Also, so I mentioned having an alternate for homework 4, so you can do a regular assignment, or you can do the coding option, which is implementing what I'm going to cover today, actually, the symmetric QR algorithm. So I've gone ahead and posted that. So in Canvas, you can go under where homework 4 is, so it has both versions of the assignment there now. So there's a 2-page PDF that describes, like, here are functions that are to be written. There's a couple functions that I've provided, like for implementing household or given rotations. So those files are there too. And also my regular site, bless you, Walker. So, I may not have heard it, but so,
Much appreciated.
okay. And so on my site on the assignments page, you'll find it there. So, so you can do either one. So I have to have everything in by. Actually, I'm gonna check this. What is the deadline for getting final grades in? Academic calendar. Oh, okay. Wait. Okay, this is odd. Okay. Now, usually the way it happens is you have finals week, and then the Monday after finals week is when grades have to be in. Not so this time. Finals week is April 26th to 30, and then the following week there's various commencement ceremonies, and then the Monday after that, so Monday, May 10th, is when grades are due. So I would say that the preceding Friday, May 7th, which is like well after finals week is over, is when I am able to accept submitted work and get it graded in time. So, okay, so then you guys have a little more time than I thought. So really, that's your effective due date for everything.
Will that be for PDE as well? I know I'm jumping the gun, but
yes, it will. Yeah.
Okay.
Yeah, and I think there are some people in PDE who definitely need that amount of time. So, okay. What's this? That might happen anyway, but so, all right. Well, I think we'd be pretty close to it. Okay, now just out of morbid curiosity. Okay. Class is not a democracy. Nice try, Taylor. Let's see. I can say that for everyone in PDE and almost everyone in this class who has submitted work, not everyone has an A average on that work. Now, some people have turned in more things than others, so I've not filled in zeros for undone things just because you don't have time for that. But so generally people are in good shape. But those who have not turned in work, and there's a non-negligible number of people in that category across the two classes, that needs to be remedied. But at least there's more time, till May 7th to make that happen. Okay, so as much support as there is for giving everyone A's, it might turn out approximately that way anyway. We'll just see what happens. Okay, now to the notes. All right. Oh, that's totally the wrong date. All right. So last time I finally got to the end of describing algorithm, a QR algorithm for computing the eigenvalues, or really the Schur decomposition which includes the eigenvalues of a general square matrix. So there are no other assumptions there. But now we're going to look at a special case of this for when the matrix A is symmetric, that drastically simplifies certain things and allows for a lot of speed up. Okay. Okay. And symmetric case is particularly important because that will set the stage for the singular value decomposition SVD algorithm that'll be coming on Wednesday. Rachel, I appreciate your concern about my grading load. So, since grading is my least favorite part of a job for me, so I've learned to become extremely fast at it. Of course, generally trying to err on the side of generosity. Okay, so yeah, if our matrix A is real and symmetric, or in the complex case, if it's Hermitian, so A equals its own Hermitian transpose, then how do things get nicer in this case? So here's for Schur decomposition of a Hermitian matrix. So Q transpose Q Hermitian, QT Q Hermitian transpose, where so T's upper triangular and its diagonal entries are the eigenvalues, and Q is a unitary matrix. So Q times QH is identity. So this is allowing for a case of real or complex. Now, if A is Hermitian, then what ends up happening is, I'll fill an intermediate step here. Dang thing. Okay. So if I just take the Hermitian transpose of both sides of this equation, then what I get is a Hermitian transpose is equal to, so I take the Hermitian transpose of this product. Transpose of a product is a product of a transposes in reverse order. I really think there hasn't been a single class period where that property has not come up. So QHH would just be Q. And then I have TH. And then QH. So if A and AH are equal, then these must be equal. And what you can do is I can multiply both sides. If I set these equal to each other, I can multiply on the left by QH to cancel out the Q's. I can multiply on the right by Q to cancel out the QH's, because Q is orthogonal or unitary. And the result is that T is equal to its own Hermitian transpose. So if A is Hermitian or symmetric, then so is T. But T is upper triangular. So this is upper triangular. Transpose is lower triangular. So the only possibility left is that T must be a diagonal matrix. Now, so what we end up getting is this situation. So the upper triangular matrix T reduces to this diagonal matrix D. And this is a similarity transformation that yields a diagonal matrix. So A is diagonalizable. Q is a unitary matrix, so we'd say it's unitarily diagonalizable. And we'd already seen this in the case where the matrix A is a normal matrix, and being symmetric or Hermitian is a special case of that. But now there's something more, which actually makes an even bigger difference when it comes to, oh, funny. Sorry, I just saw what was in the chat. Okay, so now Hermitian transpose, that involves complex conjugation. So if T is equal to its Hermitian transpose, then the diagonal entries of T must equal their own complex conjugates. Because remember, Hermitian transpose is transposing and complex conjugation. So when a complex number equals its own conjugate, the only way that can happen is if it's real. So that means that the eigenvalues are real, and that is going to make a big difference in terms of simplifying the QR algorithm. So we can impose an ordering on the eigenvalues because they're very comparable. So if A is a Hermitian matrix, then these are the eigenvalues, and we'll assume that we'll call lambda 1 the largest one. Not necessarily magnitude. I mean, these could all be negative, for instance, but that's the largest, and lambda n is the smallest. Now, there's a theorem called the Coront Fischer Minimax theorem that is a helpful characterization of all the eigenvalues. No, stop it. Okay. Sorry, Microsoft was annoying me. I'm sure you can all relate. Okay. So this is what the Coront Fischer Minimax theorem says. That it gives this equation for the kth eigenvalue lambda k in terms of this expression, which we've actually seen this before. This is called a Rayleigh quotient. So, so anytime you take a vector, a non-zero vector, y, and compute this, when y is an eigenvector, this expression turns out to be the corresponding eigenvalue. Now, this is a lot to digest here because we're taking a max of a min of this Rayleigh quotient. So what does this actually mean in words? I'm not sure how this will help, but okay. So what you do is you consider all subspaces of dimension k, and then over each one of those subspaces, you minimize the Rayleigh quotient. And the dimension of a subspace that you're considering is the rank of the eigenvalue you're looking for. So that's if you look at a couple extreme examples, suppose k is equal to 1. We're considering all one-dimensional subspaces. So then, what you can do is you can consider, a one-dimensional subspace would only consist of a single direction. So all the vectors in this one-dimensional subspace are parallel to each other. So then there's only one possible value of a Rayleigh quotient. In other words, the min is inconsequential because there is only one value. But then you're taking the maximum over all those values. Well, that's going to be the largest eigenvalue. So that's lambda 1. So that's the case k equals 1. The other extreme is k equals n, the dimension of a space. So now you're taking a maximum over all n-dimensional subspaces. Well, there is only one n-dimensional subspace of Rn or Cn. That's the whole space. So now the max becomes inconsequential because there's only one thing to take a max over. Within that whole space, you're taking the minimum of all possible Rayleigh quotients. So that's going to give you the smallest eigenvalue, lambda n. So k between 1 and n gives you the in-between cases of eigenvalues that are neither the largest nor the smallest. So, so what we can see from that, as I described, that the absolute maximum of a Rayleigh quotient is the largest eigenvalue. And then the absolute minimum of Rayleigh quotient over all whole space is the smallest eigenvalue. Any eigenvalue are critical points of a Rayleigh quotient. And I mean this in a calculus sense. So let me elaborate on that here. The gradient a Rayleigh quotient is 0 when the vector you're evaluating a gradient at, y, is an eigenvector. So if you were to actually go ahead and take the gradient of this, you take all partial derivatives of this with respect to the components of y. So you're thinking of this as a function of the components of y, and you take the gradient and you set the gradient equal to the 0 vector. What you find is that it's only equal to 0 if y is an eigenvector. And the value of a Rayleigh quotient is a corresponding eigenvalue. And this leads to some algorithms for finding eigenvalues of a symmetric matrix based on trying to find local maximum or minimum of a Rayleigh quotient. All right, so this is something that has no counterpart really when it comes to unsymmetric matrices. It's only in the symmetric case. All right, and Rayleigh quotient will lead to one algorithm for finding an eigenvalue of a symmetric matrix, but I'll get to it in a little bit. Now, what do we have a perturbation theory or sensitivity of a symmetric eigenvalue problem? All right. The one theorem we saw about perturbation theory in the unsymmetric case is the Gershgorin circle theorem or Gershgorin disk theorem. When the eigenvalues are real, you don't really need Gershgorin disks. You have basically Gershgorin intervals. All right. So just because the eigenvalues are real. So here we have a symmetric matrix, and here are the actual eigenvalues to a few decimal places. So the Gershgorin intervals are intervals that are centered at the diagonal entries. So 14, 4, and minus 10 are centers. And then the radii of these intervals come from the absolute values of the off-diagonal entries. So for instance, in this case, we have the last row. The sum of the absolute values is 4. So x values between 10 and 18. So 4 less than 14 and 4 more than 14. So 10 and 18. That means an eigenvalue may be in this interval, and then you consider these intervals too. Now remember, for Gershgorin theorem, it only says that the eigenvalues fall within the union of these sets. So we look at the unions of these intervals, because these intervals certainly can overlap. Then let's see, do they in this case? One. Actually, in this case, they do not overlap. So the union of these intervals holds all the eigenvalues. Now, in this particular case, we happen to get one eigenvalue per interval, but that does not necessarily happen in general. In this case, the eigenvalues happen to be fairly close to the diagonal entries. Now, for another result about sensitivity of eigenvalues, the fact that they are constrained maxima of Rayleigh quotient leads to this result. All right, so lambda I of A then refers to the ith largest eigenvalue of whatever matrix A is filled in here. So that's the notation we need for this next theorem. All right, it's called the Wieland-Hoffman theorem. So suppose you take a symmetric matrix A, and then you perturb it to get by a symmetric matrix. So E is also symmetric. So when you make this small change in A to get A plus E, how much do the eigenvalues differ? Well, it turns out that is related to the magnitude of a perturbation E. So the sum of squares of all the deviations in the eigenvalues between the two matrices is less than or equal to the Frobenius norm squared of E. Now, and this is the sum of all the entries of E squared by the definition of a Frobenius norm. So if E is pretty small, then you can safely say that the total deviation in the eigenvalues is also small. But this does not help with finding out how much individual eigenvalues change, because notice we're summing from 1 to n, so this covers a total change in the eigenvalues. But we do have another theorem about changes in individual eigenvalues. This one right here. So the difference between any eigenvalue of A plus E, so the kth largest eigenvalue of A plus E versus a kth largest eigenvalue of A, is bounded above and below by the smallest and largest eigenvalues of the perturbation E. This result can be used to prove this one, that the so a change in the eigenvalues is bounded in terms of a 2 norm of a perturbation. So again, if you have some idea as to the size of a perturbation, like if it's very small, then the kth largest eigenvalue of a matrix also undergoes a very small change. And this is pretty nice because we've seen there are situations where a small change in the input can lead to large change in the output. Like for instance, if you're solving AX equals B and A is ill-conditioned, a small change in A or B could lead to a very large change in X. We don't really see that happening here. Here we're making a small change in the matrix A, and it's not really leading to an unduly large change in the eigenvalues. That the change in the eigenvalues is closely related to the size of a perturbation. So it's a rather well conditioned. Okay. All right. Oh, just saying how you get the second inequality, because this change is bounded by these two, that whichever one is the larger of these two eigenvalues, like depending on whether the eigenvalues are positive or negative, would be the spectral radius of E. The spectral radius of a matrix, though, is always less than or equal to its norm. And I mean whichever norm you're using. So that's how the second inequality follows from the first one. Proving the first one I actually left as a homework problem, although I did not assign that one, but it is one of the explorations in this section. Now, speaking of conditioning, I've talked before about the condition number for an eigenvalue, and a formula was derived for that. It was the angle between the, or it's 1 over the cosine of the angle between the left and right eigenvectors for that eigenvalue. So what happens in the symmetric case? It works out very nicely. So if the matrix is symmetric, or even if it's a normal matrix, not necessarily symmetric, the left and right eigenvectors are the same. So the cosine of the angle between them, if the angle between them is 0, so cosine of 1. So the condition number of an eigenvalue of a normal or symmetric matrix is always 1. So we could say that at least simple eigenvalues, so non-repeated eigenvalues, are perfectly conditioned. So they're quite insensitive to perturbations, which is backed up by the theorems I showed you previously. But there's always a but. Eigenvectors of symmetric matrices can still be sensitive to perturbations, and the reason why is what controls the sensitivity of eigenvectors is the clustering of the eigenvalues. Well, a symmetric matrix can have eigenvalues that are just as clustered as any other kind of matrix. So eigenvectors may still be ill-conditioned. Now, the thing is, because any symmetric matrix is diagonalizable, you're never going to have a defective eigenvalue. Like if I have an eigenvalue of multiplicity, say 5, then there will be 5 linearly independent eigenvectors for that eigenvalue. Another way of putting it is the geometric and algebraic multiplicities of eigenvalues of a symmetric matrix are always the same. But still, a small change in a symmetric matrix could still lead to a large change in invariant subspaces. So that's something to be aware of. So it's not perfectly conditional all the way around. Okay. So what can be said about how much a invariant subspace changes when a matrix is changed? Okay, so suppose we have this matrix as R columns. So it's a rectangular matrix. So it's tall and thin. So R would be less than N. So orthonormal columns. So we have this relationship here. Now, if these columns span an invariant subspace of A, then we have this relationship that came up before when talking about invariant subspaces. AQ1 is equal to Q1S. So this is synonymous with invariant subspace. That always happens in this case. And now we actually have a formula for S in this case. It's Q1 transpose AQ1. All right. Now, what if Q1 does not form an invariant subspace? So we do not have a relationship like this. We have something left over. We can think of this E1 as some kind of error. So it can be shown, and I won't get into all the details here, but that it can be shown that Q1 is an approximate invariant subspace, and basically the magnitude of the norm of E1 gives an indication of the error in this approximation. So what we can say is that if the norm of E1 is small, so if AQ1 is almost equal to Q1S, then this matrix S is R by R because Q1 is R columns. So the R eigenvalues of S turn out to be close to selected R eigenvalues of A. Now, the eigenvalues of S are called Ritz values of A. Because they come from eigenvalues because they're the eigenvalues of matrix of this form that's obtained from A. The eigenvectors of S are called Ritz vectors. So we can say that if this relationship does not hold, but it approximately holds, like we have some small error left over, then the eigenvalues of S at least well approximate selected eigenvalues of A. Some terminology here. If theta k is an eigenvalue of S, and UK is the eigenvector that goes with it, so that's an eigenpair of S. But in relationship to A, it's called we have a Ritz pair. So the eigenvalue is the eigenvalue of a Ritz pair, and then this eigenvector we multiply by Q1. So that is a Ritz pair of A. So theta k is an approximate eigenvalue of A, and yk is an approximate eigenvector. Now, one case of particular interest is if the columns of Q1 they're orthonormal, they form a basis for a Krylov subspace. So if you take like the first column of capital Q1, that's little q1, and keep applying A to it, that builds up a Krylov subspace. And how you get those columns of Q1 from this Krylov subspace, we've seen that before. That's the Lanczos algorithm. So Lanczos iteration generates an orthonormal basis for this Krylov subspace. So we saw that before. So what that means is there's a relationship that comes from Lanczos. So AQ1 is Q1 TK. TK is a tridiagonal matrix that comes from the Lanczos algorithm. And it actually is defined this way. So it's playing a role of a matrix S from the earlier discussion. And this is capital E1. This is what's left over. So now, if I get the eigenvalues and eigenvectors of TK, so that's here we have a short decomposition. So capital theta here, that is a diagonal matrix that holds the eigenvalues of TK, which are Ritz values of A. And then U is a K by K orthogonal matrix. Orthogonal matrix. So what we know is that Yj, the Ritz vector, is an approximate eigenvector of A. Now, if it wasn't a true eigenvector, this would be 0. It's not 0, but it is bounded by this. So if you run the Lanczos iteration and you get to a point where beta k is small, then that means that the Ritz vectors are very good approximate eigenvectors of A, and the corresponding Ritz values of theta j are excellent approximate eigenvalues. In fact, if Lanczos iteration is run to a point where a beta is 0, that's a very welcome development because it means you have a true invariant subspace. And that means you have selected eigenvalues and eigenvectors of A. So that's one way to solve the symmetric eigenvalue problem. And you choose an initial vector, little q1, keep running Lanczos iteration until beta k. Now, sorry, I should have made this clear earlier. This comes from the notation from Lanczos algorithm. The tridiagonal matrix TK had the alphas along a diagonal, and then the betas above and below. That's what I'm referring to here. So if one of these subdiagonal entries of TK becomes small, then you stop the Lanczos iteration, and you get the eigenvalues and eigenvectors of TK, which hopefully will be much smaller than A. And that will lead you to very good approximate eigenvalues and eigenvectors of A. And in fact, it has been proven that the extremal eigenvalues of TK, which are extremal Ritz values of A, are very good approximations of the extremal eigenvalues of A. So by extremal, I mean largest and smallest in magnitude. So the interior eigenvalues, Ritz values, not so much, but the extremal ones are very good. So this is a very good approach to getting the largest or smallest eigenvalues of a symmetric matrix is to use Lanczos iteration. So like if that's all you're interested in getting. So if it analyzed, how does this compare with using a power method? Because a power method, we already know, is capable of getting the largest eigenvalue of a matrix, but Lanczos does so more effectively in this symmetric case. All right, for questions up to this point. All right, and that's all for sensitivity analysis. We'll look at actual algorithms now. Now, in this unsymmetric case, we first solve a power method that could be used to get a select eigenvalue, the largest one. So we'll start in the same way here. Rayleigh Quotient iteration, which is closely related to the power method, can be used to get selected eigenvalues of a symmetric matrix. And then I'll get to the QR algorithm for getting all the eigenvalues, but that's more expensive, of course. Okay. Now, speaking of a power method, if you do apply it to a symmetric matrix, it's actually a lot more effective than for a general square matrix, because the convergence rate is what before it was lambda 2 over lambda 1, but then you square that for a symmetric case. So here, if this number is supposed to be less than 1, so if you square it, of course, it's going to be smaller. So it converges a lot more rapidly than for a unsymmetric matrix that has the same eigenvalues. But now we can speed it up even more using approach I mentioned before. It's inverse iteration. So inverse iteration is a power method applied to A minus mu I inverse, where mu is some chosen shift. So if lambda 1 and lambda n are the eigenvalues of A, but the eigenvalues of this matrix, we subtract this shift, and then because it's the inverse, we take 1 over them. So these are the eigenvalues of the shifted inverse. So if we apply the power method to this matrix, we're going to find the largest of these. Well, that means the denominator has to be as small as possible. That means that lambda I has to be close to mu. So that's the eigenvalue that inverse iteration will find, assuming it's unique. And if you have two eigenvalues that are equidistant from mu, then like exactly equidistant, then inverse iteration will fail for the same reason that the power method would fail if you have the largest eigenvalues of equal magnitude. Okay. So here's the algorithm. Not a whole lot to it in terms of steps. Okay. So we choose some unit vector to start, and the shift is provided as input. So each iteration, you just go ahead and solve this system of equations. You're solving an AX equals B problem, and yes, that can be expensive. And then the solution that you get, zk, you normalize it. So these sequences of x's are unit vectors, and they will converge, hopefully, to an eigenvector of A. And the corresponding eigenvalue will be the eigenvalue of A that is closest to whatever you've chosen for mu. Now, what I've described here, we choose a shift at the beginning, and then we keep using that shift. What if instead we allow the shift to vary? That every time we generate a new x, we take the Rayleigh quotient. Because remember, if x is an approximate eigenvector, Rayleigh quotient will be the corresponding approximate eigenvalue. So then we get this algorithm called Rayleigh quotient iteration. So again, we choose some initial vector, unit vector. So then each iteration, we don't have a shift given to us. We compute it by taking a Rayleigh quotient. Now, in this case, I don't need the denominator of a Rayleigh quotient. Well, actually, can anyone tell me why I don't need to include that? And this is still the Rayleigh quotient, but how come I did not need to divide by xk transpose xk? Think about whatever properties xk has as shown here. Anyone? Take a guess.
Can you repeat the question?
How come I do not need to actually include the division by xk transpose xk, and it still gives me this?
Because the product of vectors is just a number.
Well, it is a number, but the focus here is on what that number is in this case.
Isn't it because the norm is 1?
Yes. So what happens is, because keep in mind, x transpose x, that is the 2 norm of x squared. Well, the norm of the xk's is maintained to be 1. So your initial guess needs to be a unit vector. And every time we compute a new one, we normalize this vector zk. So every xk is a unit vector. It has a 2 norm of 1. And since we're dividing by the 2 norm squared and we know that's 1, we don't need to include it. Now, it can be shown that if the method converges, that's not a guarantee, but if it does, it converges cubically to an eigenvalue-eigenvector pair. That's huge because I've shown you quadratic convergence before. We've already seen that can be pretty fast. Cubic convergence is faster still. So you only need to run this algorithm a few times, very few iterations to get an excellent approximate eigenvalue, which is good because each iteration is expensive because you're solving an AX equals B problem. All right. Inverse iteration of what I'm using it here for symmetric matrices can be used for a general square matrix, even if it's not symmetric. So in an unsymmetric case, if you compute a Schur decomposition, you get the eigenvalues. You don't have the eigenvectors yet. But you could use the eigenvalues that you get in the Schur decomposition as the shift. So because it's already like extremely close to an eigenvalue, like it only differ from one by round off error, then you carry out inverse iteration as I've described here with that computed eigenvalue as the shift. Now this matrix would be very nearly singular, but it would still be technically non-singular. So you could solve this system and maybe only just perform one iteration, and then you have an excellent approximate eigenvector. So that's what happens in practice. Just one iteration is enough when your shift is that close to an eigenvalue. Okay, but if you don't have eigenvalues handy, you just have to take a guess at the shift. You could still try using it for a unsymmetric matrix, but it's better for a symmetric one, just because of power. You're using a power method. That's what inverse iteration is, a power method applied to a shifted inverse matrix, and that converges much more rapidly in a symmetric case, as I mentioned a little while ago. A good rule of thumb is that if you only want selected eigenvectors, like let's say you want maybe 25% of the eigenvectors or less, then it's a good idea to use inverse iteration. Like after you go through the QR algorithm and you get the eigenvalues, you get the Schur decomposition, then inverse iteration is good for the computing whatever selected eigenvectors you need. If you really do want all of the eigenvectors and your matrix is not symmetric, after you compute the Schur decomposition by the QR algorithm, if you want all the eigenvectors, then that takes a lot more work. And I'm not covering that procedure. It's honestly, it's pretty ugly. Okay, so there are a couple of methods for getting selected eigenvalues of symmetric matrix. Now, if you want all of them, of course, we have the QR algorithm. I'm just going, and so you could use the QR algorithm pretty much exactly as described before in the unsymmetric case, but I do want to talk about certain simplifications that are made because of the symmetry. And those simplifications are quite substantial, in fact. And this is a big reason. If you have a Hessenberg matrix that we dealt with in the QR algorithm before, if it's also symmetric, then it has to be tridiagonal because a Hessenberg matrix is 0 below the first subdiagonal. So if that portion of a matrix, when flipped, is also 0, so anything above the first superdiagonal, that leads to a tridiagonal matrix. So if you recall, the first step in the QR algorithm in general is to take your matrix A and reduce it to Hessenberg form using householder reflections. Well, in that case, that will give you tridiagonal form when it's symmetric. But one nice thing is because it's symmetric and because you know the result is going to be tridiagonal, you don't have to perform as many operations. You know you're going to wind up with only at most 3 non-zero entries per row and column. So that can get you out of having to perform some of the computations that you would need to do in the unsymmetric case. Now, once you have reduced A to tridiagonal matrix T, and then you're going to continue working on that, just like you would work on a Hessenberg matrix before, what happens? Because you're going to compute the QR factorization and multiply the factors in reverse order, so that part's not going to change. So suppose T is symmetric and tridiagonal. So you go ahead and compute the QR factorization. Q turns out to be upper Hessenberg, and R is said to be what's called upper bidiagonal. What that means is there's only 2 non-zero diagonals. That's the bi. The main diagonal and the one diagonal above, so one super diagonal. And that's the only part that is non-zero. So R in this case has a upper bandwidth of 1 and a total bandwidth of 2. And one really nice thing is, then when you multiply the factors in reverse order, like in the QR algorithm, the result is also tridiagonal. So just as in the unsymmetric case, Hessenberg form was preserved, here tridiagonal form is preserved, which makes sense because you're preserving symmetry and you're also preserving Hessenberg form. And because you have both, it means it has to remain tridiagonal too. Now, one huge gain in efficiency in a symmetric case is because it's tridiagonal. When you perform a Gibbons rotation, you're rotating rows or columns. As I mentioned earlier, there's at most 3 non-zero entries per row or column. So each Gibbons rotation affects only order 1 non-zero entries. In other words, it's not proportional to n. So then the compute the QR factorization of a tridiagonal matrix is order n squared operations if Hessenberg. But if it's Hessenberg and symmetric, therefore tridiagonal, it's order n. So in other words, a whole order of magnitude reduction in the amount of work taken, the amount of work needed to compute this QR factorization, and then also compute RQ. So order n squared in the unsymmetric case becomes order n work in the symmetric case. So that makes the QR algorithm a whole lot faster in the symmetric case. But if you also want the eigenvectors, then you have to keep applying those Gibbons rotations to update your orthogonal matrix and your Schur decomposition. So that will still take just as much work as before. So you're not getting any gain there compared to the unsymmetric case. Now, the implicit Q theorem also applies in a symmetric case. So if you have a tridiagonal matrix, if you have a symmetric matrix A, and you have two ways to reduce it to unreduced tridiagonal forms. So in other words, all the subdiagonal entries are non-zero, just like how we had unreduced Hessenberg matrices before. They have the same first column, then they're essentially the same. All of that would apply just as much as the unsymmetric case. Nothing would change. Now, in the unsymmetric case, the reason we needed the implicit Q theorem was to be able to compute complex eigenvalues efficiently. Now, in the symmetric case, we don't have any complex eigenvalues. So that whole elaborate double shift strategy, or actually it was the implicit double shift strategy I described last time, that led to the Francis QR step, don't need any of that now because the eigenvalues are real. So you can just use a single shift strategy. But the implicit Q theorem is still useful, even if it's not as essential as before. That you can carry out the similarity transformation you need in each iteration, so like compute QR and then RQ, and you never have to explicitly form T minus mu I. Or this is a matrix that you're working on, and mu is whatever shift you're using during that iteration. Because what you can do instead of computing the whole matrix T minus mu identity, you just compute the first column. And that only has two non-zero entries because T is tridiagonal. And you're just subtracting mu from a diagonal entry. So then you come up with a Gibbons rotation that will zero out this column except for the first entry. And the reason why we do that is okay, I need to explain this here. Whoops. Oops. So the reason why we're doing that is that's how you start computing the QR factorization of this matrix. So then you figure out what transformation that would be, but you don't apply it to this matrix, you just apply it to T. Now that's going to wreck the tridiagonal form. So then you use additional Gibbons rotations to make it tridiagonal again. Now, one of the homework problems that I actually have assigned for this section is to describe how this process actually works. How do you choose which Gibbons rotations you need to eventually get this matrix to be tridiagonal after you've messed it up by applying this transformation to it? So I want to describe to you how you would actually give your answer to for this homework problem, like in terms of notation. So what you can do is write out a generic tridiagonal matrix where you just use X's to indicate where the non-zero entries are. So here we have an ordinary tridiagonal matrix. So then the first step is you come up with some Gibbons rotation, and because it's working on the first column of T minus mu I, it is a column that has only two non-zero entries. So that means your Gibbons rotation, you're trying to zero the second entry. So it's going to work on rows 1 and 2. So if you apply Gibbons rotation to rows 1 and 2, how would this structure be affected in terms of what entries are non-zero? Like, in other words, if I do this given rotation applied to rows 1 and 2, what new non-zero entry is introduced? In other words, like, where is it? So I want you to tell me, and then I'll mark it on here. If I give for a given rotation of these two rows, is remember when you do a given rotation of two rows or two columns, each row or column is becoming a linear combination of the two things you're rotating. So if each row of these two is now some linear combination of these same two rows. In other words, so the rows 1 and 2 will become linear combinations of themselves. So can anyone tell me, like, by indicating like row and column, if it's a 5x5 tridiagonal matrix, where there would be a new non-zero entry introduced? So everything is happening up here. So what entry that was 0 before could become non-zero because of doing this rotation of these two rows?
Would it be one? Would it be the one in the 1-3 position?
Yeah, row 1, column 3. So I'll go ahead and put it in here. Oh, that's weird. It's supposed to be in color. Well, it should be in color in the PDF when I post it later. For some reason, it's not honoring that here. Yeah, so because what happens is the first row is a linear combination of the first two rows. And we have this non-zero entry down here. So that's going to be multiplied by something like a sine or a cosine, and that'll be filled in here. The second row also is a linear combination of rows 1 and 2, but because of which entries are non-zero in those rows, there aren't going to be any new non-zero entries introduced here. So there's just this one. So then what you'd want to do is okay. Now, let's see. So after that, what you want to do is apply more givens rotations, either on the left or the right, to restore tridiagonal form. So something has to be done about this entry. Now, but the thing to keep in mind is any given row rotation must be balanced. Say rotation applied on the right to rotate those same columns. And that's going, so that will have the effect of preserving symmetry. Okay. So what will happen is, and also not just preserving symmetry, you have to be performing similarity transformation. Anytime you multiply on the left by a certain matrix, you have to multiply by the inverse of that matrix on the right. Now, a given row rotation is orthogonal, so that means you're multiplying on the right by the transpose. So what would happen is, if now you apply rotation on the right, it would be applied to columns 1 and 2, and that will introduce a non-zero entry right here in the 3-1 position. So that first transformation that's designed to compute the QR factorization of T minus mu identity has the effect of introducing these 2 non-zero entries here. So then you want to work on that, figure out what rotations are needed to restore tridiagonal form. And what you can do for this homework problem is try out this 5x5 case, like follow it through to its end. Like after you get a column rotation that produces something right here that you don't want, then you do more given rotations, again, of the left and right. And the thing is, if you do something on the left that will zero an entry, then applying that same rotation on the right to columns will also zero the opposite entry. So that's something to keep in mind, is that to preserve symmetry. So try it out and see what happens. Like if you get rid of an entry you don't want, like you zero it out, then what happens? Then then you're going to get a non-zero entry, an unwanted non-zero entry somewhere else, and then you got to deal with that, and so on and so forth. So so try this out in a small case and see where it leads. Any questions about what happened there?
Will we need to use actual numbers to see that happen, or is it possible to see it with just position pieces like you're doing now?
You could do what I'm doing. I mean, yeah, if you want, you could try conning something random in MATLAB, but that's more trouble than you need to go to. Because, like for example, okay, so because what will happen after this first transformation that I showed you here, like here's after applying to the rows, and then and then because rows 1 and 2 are rotated to get this, and then columns 1 and 2 are rotated to give this. Actually, I want to put that in color too for when I make the PDF. From this point forward, your rotations will be specifically designed to zero entries of this matrix. Like what happened before was you come up with a given rotation that's meant to zero an entry of one matrix, and then you apply it to a different one. And severity effects are a bit unpredictable. But from this point forward, you're saying, okay, I want to come up with a given rotation that will zero this entry. So then this X will go away. And then when you apply that same row rotation, that will have, after you do row rotation that zeros this entry, you can do the corresponding column rotation that will zero out its mirror image, this entry. If you choose your which rows and columns you rotate carefully. That's one thing to keep in mind. Because like if you do a given rotation of you're saying, okay, it rotates this row and this row, it only affects those two rows. and then when you apply it on the right, it'll affect only those two columns. So then you can say, okay, now I can make something that will make this go away and this go away. Those x's are gone, but what new x's will appear, and where will they be? That's the thing to find out. Yeah, normally when I teach this class on the board, I'd be drawing all kinds of matrices like these and drawing in all these x's, and it got old after a while. Any further questions about this? I still have a little more cover, but I only have a few minutes left. Now, we don't need a double shift, as I mentioned. You can use a single shift. Now, in an unsymmetric case, a single shift was just the NN entry. So you can use that. But in a symmetric case, there's actually a better choice. It's called the Wilkinson Shift. And this is a formula for it. The other homework problem for this section is to derive this formula from a quadratic formula. Now, what is the definition of this Wilkinson Shift? It's you take the lower 2x2 block of your tridiagonal matrix T that has these entries, n minus 1, n minus 1, and nn, and then nn minus 1. And then you find its eigenvalues. Now, it's the eigenvalues of a 2x2 matrix that can be found using a quadratic formula. But this is choosing the root that is closer to TNN. And that's what leads to like this expression right here. Sine of D is 1 if D is positive and minus 1 if D is negative. This actually leads to cubic convergence. So subdiagonal entries are zeroed out even faster than the quadratic convergence we saw in the unsymmetric case. That was already quite good, but this is even better. So this ultimately what we can say is that symmetric QR algorithm is a whole lot faster in the unsymmetric case because there's so much less expense to doing a QR factorization. The shift leads to faster convergence. So a single QR step only requires order n iterations instead of n squared. Now, if you are accumulating orthogonal transformations to get eigenvectors, then you're doing order n squared work. So the overall algorithm is order n cubed. Most of that comes from reducing A to tridiagonal form T up front before the iteration even begins. And then there's much extra work if you want the rest of a Schur decomposition. And because it's symmetric, once you compute a Schur decomposition, the columns of Q from your Schur decomposition are the eigenvectors. So there's no extra work to do there. So that's one of the main benefits of a symmetric QR algorithm. It gives you the eigenvalues and eigenvectors, whereas unsymmetric case, you get the eigenvalues and the Schur vectors, which are not eigenvectors. So that would take some extra post-processing, actually a lot of extra post-processing if you want the eigenvectors in that case. Okay, so that's all I have to say about the symmetric QR algorithm. So then on Wednesday, I will show how ideas from this algorithm can be used to compute the singular value decomposition of a matrix. And this was my advisor's the biggest achievement of his career. Okay, so out of time. Of course, I'll stick around before PDEs, and I'll see some of you there. In case anyone has any questions, but I will stop recording at this point.